A great day to one and all. So, supposedly, the topic that we will be having for today should be in the fourth grading period. But because we are fast enough in our pace, and then we will have this topic in the third grading period. And the third and the remainder of our lessons from now on will be all about statistics and probability. Suppose, but for now, let us discuss about counting techniques. Suppose you have three shirts, men's club, bench and Adidas, and two pairs of pants, which are Jag and Paddocks. How many outfits consisting of a shirt and a pair of pants are there? So there are many ways of doing this. You could either make a diagram, a tree diagram. You could list all the possible outcomes, but for now, we will make this diagram. So I have here on the left, the three shirts, which are men's club, bench, and Adidas. And I have here on the right, your Jag and your Paddocks or your pair of pants. And by connecting them, for example, like this, I could have men's club and Jag. Exhausting everything for men's club, we also have men's club with Paddocks. We also have bench to Jag, bench, Paddocks. We have also your Adidas and Jag and your Adidas and Paddocks. And I believe there are no more other possibilities, right? And hence, we could see that there are 6 combinations of outfits consisting of a shirt and a pair of pants. But without listing, you could actually see that there are 3 here, 3 choices for shirts and 2 choices for pants, and they give you 6. And without noting all possible outcomes or without actually listing all of them, how do we get the total number of outcomes? We could see here that what we did with 3 and 2 to get 6 is we multiplied them. And that you have here 3 times 2, which is 6. That means if you have 3 shirts and 2 pairs of pants, then there are 6 possible outfits consisting of a shirt and a pair of pants. With that, without actually listing everything, we could determine the total number of outcomes using what we call the fundamental counting principle. And this principle states that if an independent event can occur in m ways, while the other can occur in n ways, then there are mn combinations for them to occur together. In other words, that is, if m is the number of ways for the first independent event and n for the other independent event, then their occurrence together is simply taken by multiplying their cardinalities of each independent events. So there are many ways, no? We could actually create, as what I mentioned, we could actually create a table. We could use listing. We could also use the tree diagram method as what you have learned when you were in grade 8. But for now, we will utilize the slot method to answer problems that involve the fundamental counting principle. Example. Nasyo has 3 gates, 1, 2, and 3. Gate 1, gate 2, and gate 3. In how many ways can you enter and exit Nasyo using any gate? Meaning, you are free to enter and exit anywhere you like using these 3 gates. So here, there are actually 2 slots. The first slot is the entrance, and the second slot is the exit. And okay, here are the 2 slots. In the entrance, in the slot for entrance, they could actually enter in 3 ways. Why 3 ways? Because they could enter in 1, 2, or 3. Gates 1, 2, and 3. And remember, according to the problem, they could exit anywhere they like. So they could also exit in either gate 1, 2, or 3. That means there are also 3 choices for exit. And by the fundamental counting principle, that's 3 times 3 or 9. Meaning to say, there are 9 possible outcomes or 9 ways for you to enter and exit na show using its 3 gates and using any gate. And you might ask, are you sure there are 9? Maybe it's good if we list all the 9. Example, no? You could have 1, 2. 1, 2 means you enter at 1 and exit at 2. Let's say we have this notation, but let's avoid the, for now, I will not place the parenthesis. So you could end when say 1, 1. 1, 1 means you enter at gate 1 and exit at gate 2, at gate 1 still. 1, 2 means you enter at gate 1, you exit at gate 2. Gate 2. 1, 3 means you enter gate 1 and exit gate 3, and so on. So you could also have 2, 1, 2, 2, 2, 3, and 3, 1, 3, 2, and 3, 3. Hence, these are all the 9 possible outcomes. All right. I hope so far so good. Now, how about if I will use the same condition na show has 3 gates, 1, 2, and 3. In how many ways can you enter and exit na show if they enter and exit by a different gate? So here, let's discuss the solution. There are still 2 slots. Why 2 slots? 1 slot for entrance and 1 slot for exit. But how many ways can one enter? There are 3 ways. Why 3 ways? You could enter either gate 1, gate 2, and gate 3. That's why 3 for entrance. However, for exit, is it still 3 or not? And the answer is not. It's no longer 3 for the exit. Why? Supposing you entered at gate number 1, then by this problem, you could no longer exit by gate 1. Hence, you could either exit at gate number 2 or gate number 3. So that's 2 possible outcomes or possibilities for exit. And by the fundamental counting principle, that's 3 times 2 or 6. 6 ways to enter and exit by a different gate. And I think 6 is just manageable. Hence, let us list all of them. So you could have the following. You could enter by gate 1 and exit at gate 2. You could also enter gate 1 and exit by gate 3. But you could notice I removed the 1, 1 because the 1, 1 indicates that you enter at gate 1 and exit at gate 1, which is not allowed considering that your entrance and exit gates have to be different. Aside from these, you could also have 2, 1, 2, 3 and 3, 1, 3, 2. And these are the 6 of them. All right. So far, so good. And it's also good to note that the fundamental counting principle is not only true for 2 slots. If you have 3 or more slots, the fundamental counting principle is still applicable. Example. In how many ways can you answer 3 true or false items by true or false, but not both? And no item should be left blank. Meaning, you have only 2 options per item. And you might ask, how many slots are there? Is there 1 slot, 2 slots, or 3 slots? 4 slots, what do you think? Remember, we have 3 true or false items. Therefore, there are 3 slots. And these are items 1, 2, and 3. And you might ask, in how many ways can you answer item number 1? There are 2 ways. It's because you will write there true or false only. You cannot write both of them. You cannot leave them blank. That's why there are only two ways of providing answers for item number 1. The same thing with number 2. You could answer true or false in number 2. And the same is true for number 3. And with this, by the fundamental counting principle, you could say that there are 2 times 2 times 2, or 8 ways for you to answer all of these 3 items that are true or false, but you cannot answer them both by true, false, and no item should be left blank. Let's list all 8 of them for you to be convinced. Take note that, example, you could have TTT. That means item number 1 is true, na item number 2 is true, item number 3 is true. You could also answer TFT, meaning item number 1 is true, item number 2 is false, item number 3 is true. And if you list everything, these are the 8 of them. We have TTT, FTT, TFT, FFT, TTF, FTF, TFF, and FFF. There are 8 of them as guaranteed by the fundamental counting principle. If you wrote 9 or more, I think that there is a big chance that you have duplicated. There's a chance, no? That you have duplicated 1 or more possibilities, because there are only 8 according to the fundamental counting principle. But don't worry. In this case, we just did them, we listed them because the 8 outcomes is just manageable. But more often than not, don't worry, because I will not let you write everything, especially if there are hundreds or thousands of possibilities. But what's important is that we know how many possibilities there are. Let's have the next one. The top 5 in the Miss Universe finale are from Brazil, Peru, India, Mexico, and Dominican Republic. In how many ways can they finish, considering that there are no ties for any position? In this case, it is understood that no repetition is allowed. What do I mean by that? Example, if Brazil is already Miss Universe, then Brazil could not be first runner-up, second runner-up, third runner-up, or fourth runner-up. So here, there are 5 slots. These are the Miss U, first, second, third, and fourth runner-up slots. And how many could win Miss U? There are 5 of them. It could be any of Brazil, Peru, India, Mexico, and Dominican Republic. So there are 5. Supposing Brazil is already the Miss Universe, then Miss Brazil is not in contention for any of the remaining 4 awards. Meaning, Peru, India, Mexico, and Dominican Republic could serve as first runner-ups. That's why there are 1, 2, 3, 4 of them. So we have 4 there. Supposing Peru is the first runner-up, Brazil and Peru can no longer vie for other awards. Hence, India, Mexico, and Dominican Republic, there are 3 of them who are possible contentions for the second runner-up. And supposing India is the second runner-up, Mexico and Dominican Republic, there are 2 of them who will vie for the third runner-up. And if it's Mexico who won third runner-up, then Dominican Republic has no other option but to be the fourth runner-up. And that's 5 times 4 times 3 times 2 times 1, which is 120 ways. Therefore, these 5 Miss Universe finale contestants can finish in 120 ways, considering that there are no ties for any position. I hope it's clear with us. Now, if you could notice in the expression 5 times 4 times 3 times 2 times 1, it seems like you multiply all the whole numbers from 5 all the way until 1. And if that happens, if you take the product of all the whole numbers from a given whole number all the way until 1, then this is represented here in this case by 5 with the exclamation point. And that exclamation point is read as factorial. Hence, the product of 5, 4, 3, 2, and 1 is equal to 5 factorial. And let us now define factorials of whole numbers n. That is, if n is a whole number, then n factorial is simply equal to the product of all whole numbers from n all the way down until 1. That is, n factorial equals n times n minus 1 times n minus 2 times n minus 3 all the way until 3 times 2 times 1. Example, if I ask you, what is 4 factorial? By using the definition, all the whole numbers from 4 to all the way to the down until 1 are 4, 3, 2, 1. So 4 factorial is equal to 4 times 3 times 2 times 1, which is 24. I hope you got 24 correctly. All right. Next one. Let's have your exercises. Let's find the exact value of the following factorials. If you have 3 factorial, that means 3 times 2 times 1, which is 6. How about if you have 6 factorial? That means you multiply all the whole numbers from 6 all the way down until 1. So 6 factorial is 6 times 5 times 4 times 3 times 2 times 1, which is 720. How about 1 factorial? I think that's kind of easier than the rest. 1 factorial means 1. But you might ask, how about 0 factorial? And when I ask some learners, they would answer it's 0. But actually, believe it or not, 0 factorial is not 0, but instead it's equal to 1. And we have to remember this, that 0 factorial and 1 factorial are both equal to 1. And you might ask, sir, how come? I'll just show you a simple proof on how we could say that 0 factorial is equal to 1. So I have here some of the factorials this way. Now, we will work backwards. Take a look at this pattern. If I divide 24 by 4, that's 6. So we have here 6. 6 divided by 3 will give you 2. So we have here 2. 2 divided by 2 will give you 1 here. 1 divided by 1 will give you 1. So you see that 0 factorial, using the same reasoning I applied with starting from 24 factorial, from 4 factorial all the way until 0 factorial, we are able to show that 0 factorial and 1 factorial are indeed both equal to 1. Now, here are some factorials. So 0 factorial is 1, 1 factorial is 1, 2 factorial is 2 times 1 or 2, 3 factorial is 3 times 2 times 1 or 6, 4 factorial is 4 times 3 times 2 times 1 or 24. For 5 factorial, the trick is simple. 24 is 4 factorial times 5 will be 120. 120 times 6, so that's 6 factorial is 720. 720 times 7, so 7 factorial is 5040. 8 factorial is 40,320. 9 factorial is 362,880. And 10 factorial is 3,628,800. For our class, since we are dealing with factorials and we are multiplying whole numbers, there is a tendency that numbers become really large. That is why I highly encourage you to secure a calculator with you If not, you may also download certain calculators or emulators of calculators from the net for your use. Because from now on, we will be dealing with large numbers. Normally, in competitions, I let my students memorize until 10 factorial at least. But if not, you could still verify them with your calculators. Now, I will give you this exercise, but try to answer them on your own. Let's have the first one. In how many ways can a doctor visit his 7 patients once in his rounds? So from here, when we say in his rounds, meaning to say for a day, the doctor will visit all of these 7 patients, but he can do this in any order that he likes, right? So we have 7 slots. So using the slot method, in the first visit, he could visit 7 of them. Suppose he visited already 1, then for the second, he could visit 6 people. And visiting again one of those 6 people, which means that he could visit 5 people on the third one, on the third visit, and so on until you have 4, 3, 2, until such time that in the last visit, he could only visit 1. So using the slot method, we have 7 times 6 times 5 times 4 times 3 times 2 times 1, or in factorial notation, that's 7 factorial, or 5,040. I hope you got this correctly. Let's have the second one. How about how many 5-letter string arrangements are there in the word mango? Mango has 5 letters. You see that there are also no repetitions in the digits or in the letters. And the total number of ways is simply using the same reasoning is 5 times 4 times 3 times 2 times 1, or 5 factorial, which is 120. So there are 120 arrangements or 5-letter strings of the word mango. And remember, it's understood that no digit or no letter rather should be repeated here. For the third one, Andy, Becky, Charles, and Daniel are joining a race. In how many ways can they finish the race if there are no ties? So if there are 4 people, since there are no ties, it's also understood that no repetition is allowed. And if you have 4 slots, 4 people could finish first place. If one of them is already first place, then 3 are viable for second place. And if the first and second place are determined, then 2 people are viable for third place, and fourth place is 1 left. That's why you have 4 times 3 times 2 times 1, or 4 factorial, which is 24. And lastly, number 4, how many 6-digit numbers are there using all of 1, 2, 3, 4, 5, and 6 if repetition of digits is not allowed? From here, using the same reasoning, you will have the product of 6 times 5 times 4 times 3 times 2 times 1, because 6 choices for the 100,000 place. Let's say you already placed 1 here. That means 2, 3, 4, 5, and 6. You have 5 options for the 10,000 place, and so on. 4 choices for the thousands, all the way until 1 choice for the 1's digit. That's 6 factorial, which is 720. Note, ladies and gentlemen, that for this case, for 1, 2, 3, and 4, the problems I give you, it's understood that no repetition is allowed here. And if ever you have questions or clarifications, please feel free to contact me from time to time. With that, thank you very much, and God bless everyone.